Okay, so one of the most confusing things in electrostatic forces, or no, electricity in general, would be what is the difference between electric force, electric field intensity, and electric potential. So I won't talk about electric potential yet. I'm going to focus on electric force and electric field first. So first of all, you need to know that there is electric field and electric field intensity. They are both different things. Electric field is what happens when you have a charge and that charge has an electric field around it. So if it's positive, it will go outwards. If it's negative, it will go inwards. It doesn't actually go outwards or inwards. It is just more convenient for us to write it that way, because normally we will use a positive test charge, and since positive charges repel, we say that the electric field goes outwards because they repel, if you get what I'm saying. But just you don't have to know why it's going outwards. You just have to know that it is going outwards if it's positive, and if it's negative, it will go inwards. Next, electric field intensity is the strength of the electric field at a given point. So for example, if I have a point here, then the electric field intensity at the given point would be kq over r squared. But I'll get more to that later. So electric field is the field around it where there is a force generated by the charge, while the electric field intensity or strength is how strong that force is on that point. Next, people might get confused between electric force and electric field intensity because they both have similar formulas. But the difference is electric field intensity is is the value of electric force per unit positive charge. So I guess the way I can explain it is, let's say you have a car, and then this car drives 5 kilometers per hour, right? And then you want to travel and then you're going to travel 60 kilometers. So you'll take 12 hours to travel with 5 kilometers per hour. A car is not that slow, but this is just an example. It's not a direct comparison, but electric field intensity and electric force act similarly to it. Electric field intensity is per unit. In the car's case, it's per hour. So the unit here is per hour. But for electric field strength, it is per unit positive charge. So in an electric field, we don't know how strong the second charge is. In electric force, we know two charges, right? We know that the both of them have a certain charge. But in an electric field, we only consider the charge of only consider one charge, the charge of the thing. So what that means is, normally when they ask questions about electric field, the second charge has, the point where we have to find the electric field strength has no charge. Do you get me yet? So let me just try to explain it in another way. As I said, when it comes to electric force, the formula is Q over R squared, where K is 9.0 times 10 power 9. This is called Coulomb's constant, and the actual calculation is 1 over 4 pi epsilon 0. I am not going to talk about 4 pi epsilon 0 because you only have to know that this is equal to this, and this is K. We call it Coulomb's constant. And for electric field strength, it is KQ over R squared. So people will ask, where did this Q go? Right? Where did this Q go? That's because the Q here is actually Q0. What we call Q0 is, we also can call it the unit positive charge. So um, I guess the easiest way to explain it will be that this is equal to 1. So when you multiply it by 1, it just joins in the equation. You don't have to care about it anymore because it's equal to 1. It doesn't change anything. So yeah, that's the easiest way for me to explain it. When we have a unit charge, the value of the unit is 1 normally. So that's how I differentiate electric field strength and electric force. Electric force is when both have charges. When we have 2 points that have charges and we want to find the force between them, the force caused by both of them. But for electric field strength, we want to find the electric strength at a given point. We want to find the force. We want to find the force exerted by the charge on a certain point per unit positive charge. Okay, it's really not that hard. I mean, it's really hard to explain it without getting confused. But one way to differentiate them is when we are calculating electric force, they will give the values of both charges. When they talk about electric field strength, they will give the strength of one electric field, but they do not give the electric strength at that point because that point has no charge. But then some of you might be asking, there are some questions where they will give you two points, and then they'll ask you to find what is the electric field strength between them. And electric field strength between them. But they will ask you to find the electric field strength between them at a given point. So because we have a point here, this electric field strength at a given point between two charges is different to the electric force between two charges, because electric force, we're talking about the overall force between those two charges. When we talk about electric field strength at a given point, we're only talking about this zone. How strong is the force when it goes to that zone? Because the force punya power at here, and here, they're all different. The closer you are to a charge, the stronger the electric field strength. But so I know. So that means if you have so that's why it's very important for you to know the point. Okay, I'm not really that good at trying to make all of you understand it as much as possible. But yeah, as I said, if you really don't get it, just know that if they don't give if they ask for electric field strength, you only need to know one charge. Unless they say that there are two charges given, then you have to add them up together. But here's the other problem. They are vector quantities. Both electric force and electric field strength are vector quantities. Why? Because electric field strength is a measurement of electric force at a point per unit charge. So because of that, we need to be more careful in calculating our answers. What do I mean by more careful? You see that there are values of positive and negative. Now, positive normally means in electric force, positive means the two charges repel each other, and negative means they attract to each other. But when we talk about resultant force, maybe one is actually attracting, one is repelling. So we cannot find a specific value, I guess. If they're both acting in different directions from each other, we can't use attract and repel because one's attracting and one's repelling. So we don't want to use that to find the final answer. So we have to be careful with the values with the magnitudes. So what do I mean by this? I'll just look at the thing that teacher gave me for teaching lessons. So let's say they want to find the force of the charge on the charge of -3 microcoulomb by the other two charges. So this is the -3 microcoulomb. So now you have two forces acting on you. One is this and this. The other one is this. So there are two forces. One is these two together. The other one is these two together. So as I said, positive and negative attract. So it will go this way. And then same thing. And then this one is also attract, so it will go this way. But you can't use positive or negative to show whether they attract or repel, because because if one attracts to this way and one attracts to the other way, you cannot use attract or repel to decide their direction, because they have a different angle of where they're going to, if you get what I'm saying. Like if it's like two charges, then you can go this way or that way, then you will know, oh, they're repelling, oh, they're attracting. But when you have two of them going together, it goes this way. You cannot use positive and negative to show your direction anymore. You need to use vector quantity. You need to do vector sum, and you have to state the angle of where it's going. So how do you do that? First of all, specify the direction of where they're going. And then number two, remove all negative magnitudes. Remove all negative signs. Make sure that your resultant force is positive. Because as my teacher would say, it will corrupt the equation. So you don't want any negative values in your calculations when you're doing it. So yeah, I'm not going to explain this. It's better for you to look at it yourself. But I will explain the resultant force thing. If you don't know already, when we're talking about vector sum, or when you're talking about vector sum, the easiest way to think about it is to think of a triangle with length. When you have a triangle with length, there are multiple ways to find the angles and to find the lengths. You can use sine rule, cosine rule, Pythagoras theorem, and I think that's the three main methods. But you have to be careful with what you use. So first of all, if you know that you have a right angle triangle in your calculations, you can safely use Pythagoras theorem to find your resultant force, because normally your resultant force is the hypotenuse. But if I believe there's some questions where it acts on a very different angle. Yeah, where it acts on an angle that is not 90 degrees. For example, maybe it's like this. Like it's bent a bit. Then you cannot use Pythagoras anymore. You need to use cosine rule. So my advice to you would be to use cosine rule all the way, because cosine rule is the safest one is your safest bet. It's not that much extra work, because Pythagoras theorem is based on cosine rule anyway. Next is you're gonna find your angle. So there are two ways to find it. Number one is sine rule, and number two is tangent. Why tangent? Because you know what your two angles are. I mean, you know what your two forces are, like the resultant force going in one direction and the resultant force going in another direction. But again, I will recommend you to use sine rule, because tangent only works if you have a right angle triangle, same with Pythagoras. So if you have Pythagoras, you can use this to answer your questions easier, but I would advise you to do sine rule. Now, just in case you don't know, I mean you forgot what those two are, I'll just tell you. So this is A, B, C, angle A, angle B, angle C, C. So the length, I mean the side facing in front of the angle is what we call corresponding. So the corresponding angle of B, the corresponding side of angle B is length B, is side B, or side of length B. So with that in mind, we have two formulas. Number one is sine rule, which is what again? A over sine A equals, A over sine A is equal to B over sine B equal to C over sine C. So that's number one. Remember, they must be right across each other, or we call them corresponding, directly opposite. Just know that there is a specific arrangement for them. Number two is cosine rule. If I remember correctly, it is A equals to B square plus c square plus, a square equals to b square plus c square plus 2bc sine, wait, they're all small letters. Why is it not erasing? Oh. So yeah, a square equals to b square plus c square minus 2, I think it was bc sine a. If I remember, this is the correct formula for this. If not, go Google it. But it's also using these sides. But yeah, you need to be careful when you're doing this. Okay, electric field is also the same thing. The calculation is also similar. Yeah, if I remember correctly, it's also similar. So you have electric field. We see here point P. The main difference with point P here and the question and the one that I did earlier, this already has a charge, -3 microcoulomb. But electric field strength, we do not care about the charge at the point, because there shouldn't be a charge at the point. Because if there is a charge at the point, that will generate another electric field. You get what I'm saying? If the point we're trying to calculate the electric field strength from has a charge, it will have its own electric field. So it will completely ruin the question. So that's why when we find the electric field strength at the point itself has no electric charge. So don't need to care about it, just have to know these two. But again, the way you calculate it is also similar. You need to make sure that you get your things right. Positive or negative. If it's positive and negative, they will go towards each other. For example, positive and negative, it will go here because negative is stronger. But if it's positive and positive, if it's positive and positive, or negative and negative, then the total strength would go outwards. If you I don't know a better way to explain this, but basically it's the same as electric force lah. If it's same charge, then the overall charge will not face each other. Sorry. Okay, if it's a positive charge, your electric field strength will go towards the charge. If it's negative, it will go away from the charge. Wait, it's the other way around. I'm sorry. But yeah, again, the reason why it's similar to electric force is because the way we find electric fields, the way we reduce the electric field in the first place is by using a positive charge. So positive repel, negative attract. But instead of saying that in electric field strength, in positive, it goes outwards. In negative, it goes inwards. So let me explain to you how do you get this answer. How do you get this, and this? Okay, first of all, we'll look at point X. So point X experiences two electric fields, here and here. X, Y, and Z are all points, and they all experience three electric fields. So X punya electric field is actually 2. So number 1 is this charge. It is positive, so it goes away from it, outwards. The second one is negative, so it goes inwards. Secondly, here, positive goes outwards, negative inwards. Here, positive outwards, negative inwards. So yeah, it's positive is out, negative is in. You don't say attract and repel in electric field strength or electric fields. You say outwards and inwards. But the reason why it's outwards and inwards is because of the attract and repel thing. That's all I'm trying to say. So yeah. Uh, so that's why you have multiple arrows. But then, how do you find the overall value? How do you know which one is bigger? You need to look at the distance. The distance between x and discharge is r, right? But the difference between x and discharge over here is 3r. So you see that they are very far away from each other. So it will be weaker. The electric field strength at that point will be weaker. So with that in mind, you can just add them together actually. So when you add them together, you can add them simply like this. The reason why you can do this difference in electric field strength is because they are both directly opposite. So same with a resultant force. If they're directly opposite each other, just find the difference between them two. If they are going the same direction, just add them both together. But again, if they are going in completely different directions, you need to use cosine rule, sine rule, Pythagoras theorem, and tangent. So yeah, I guess the way I can explain it to you again is length. If you want to find the difference between, if you want to find what is the difference between here and here, then just minus. If they're both together, you can add them together. But if they're not length, vectors. And if they're going here and here, the resultant one will be here. And the way you find it is again cosine rule, sine rule, Pythagoras. If you don't know cosine rule and sine rule, you will not be able to survive this chapter. Okay, I think I should talk about electric potential in this same video. So I'm not completely confident on my electric potential yet, but it says here, electric potential at a point in an electric field is the work done to bring a unit positive charge from infinity to the point. Okay, ignore the infinity to the point. What I will explain, how will I explain this? Okay, first of all, the formula is kq over r. So the difference here is that okay, we have kq over r squared, we have kq over r squared, and now we have kq over r. So yeah, the main difference between this and electric potential and electric field and as well as electric force would be that a potential difference is a scalar quantity. So that means you need to mention the positive or negative value. Why? Because if you the value, I mean the number, whether it's positive or negative, determines whether it is doing work or whether work is done onto it. Because remember, potential difference or electric potential is the total work you need to move a point. Okay, that's the basic example. That's the basic way to explain this. If you were to look at your SPM textbook, I think it says it. I'm gonna look at it right now. If I remember correctly, it does mention it. Okay, yeah. So, it is the work done to bring a point, to bring the potential difference is the work done to bring a 1 coulomb of charge. Okay, again, 1 coulomb of charge from one point to another. So yeah, I really don't know how to explain it that well. I'm not gonna mention this because this one is a bit too hard. But yeah, the one I didn't make a mistake. However, electric potential and potential difference are different. Electric potential is It's basically what infinity to a point. I don't know. I'm not so sure how to explain this, but they are both different, but they both are voltage. So just have to know they're both voltage. But basically, electric potential is the general consensus or the general form of voltage, of potential difference. But potential difference is when you have 2 points. So normally we will talk about potential difference, but again, they're both the same thing. They both use the same formula, KQ over R. So I don't think you have to worry much about that when they say electric potential or potential difference. If not, you just rely on the formula. You just have to know the point, and then the radius and the value. And the constant. But again, remember, you need to specify whether it is positive or negative. Positive means work is done onto the system. Negative means work is done by the system. Or in other words, if it's positive, energy is used up. Okay, if it's positive, if it's positive, the charge itself has a force to move itself from one point to another. If it's negative, it will move by itself. What do I mean by this? Remember that I mentioned that that they have that these things have magnitudes. These electric field strengths have magnitudes. Not magnitudes. Have these charges have an electric field. That's what I'm trying to say. So if your electric potential is positive, that means you need extra work. You need extra work to move the charge inside this electric field. But if your electric potential is negative, the charge will move by itself because the electric field will help it move. Do you get what I'm saying? It's kind of confusing at first, but if you just listen to my words more, you should be able to get it. Work is done onto the system means that the charge, the charge has to move with some extra help. But if it's negative, then it moves automatically. You don't need anything. You don't need to do anything to it. It will just move on its own. Okay, electric potential energy of a charge Q at a point in an electric field is defined as the work done to bring the charge Q from infinity to the point. So okay, so the way I get it is we're talking about electric potential in general. The point has no electric potential. It has no electricity. Again, it's like the electric field. That point does not have any charge. And it's not that there is no charge. It's that since we're using a unit positive charge as our charge, it's equal to 1. So if you multiply it by 1, you don't have to write it in the formula. Again, I don't know if that's going to be understandable for all of you. But basically speaking, electric potential energy is electric potential is basically how do I say this again? Okay, electric potential is when you move a specific charge. This specific charge is the unit positive charge to a point. Okay, to a point. But electric potential energy is moving is the charge. No. It's the energy needed to move a given charge from one point to another. Because as I said, if the charge is different, then it will generate its own electric field and they will interact differently. Maybe they will resist each other. Maybe they will combine with each other faster. So you need to, so it's different. So yeah, I'm really sorry that I don't know how to explain this the proper way. But I don't think people are going to watch this anyway. But I guess take it from me as some trying to think along with me and keep thinking about it in your head. So the formula for electric potential energy is U equals to QV or KQQ over R. So basically that's what electric potential energy is when you want to move a charge, an actual charge, from one point to another. But electric potential is when you want to move a test charge from one point to another and use that as reference. So that's why so when we don't have the given, when we have a point without a charge, we use a test charge as our reference. So that's why we use electric field or electric potential, electric field strength or electric potential. But when the thing does have a charge, then we use electric force and electric potential energy. And again, for electric potential energy, since it is a scalar quantity, you need to involve the positive and negative, and it shows whether it does work or whether work is done by itself. Like whether it moves by itself or whether work is done by itself or whether it needs other stuff to help do the work for it. So yeah, how do you find them? You just basically add them together. Because remember, it is scalar, the direction doesn't matter, so just add them together. So I guess that's all. Just remember I'll just give you a few extra formulas, a few actual formulas to remember. One is U equals to QV, the other one is F equals to KQQ over R square, which is equal to EE. So trust me, this is pretty significant. So the actual formula is F equals to QE, right? That's the actual formula. But what again? Normally when we solve questions, the question will ask about an electron. So the electron is your charge, but we just immediately call electron E. So we just say F equals to EE. But remember that the formula actually comes from F equals to QE. And yeah, I guess that's all. I'm really sorry. I'm not that good at this chapter either. But I guess if you just repeat what keep on going with what I said. If you still don't understand, just text me. But if not, just keep thinking about it. These types of physics questions require you to think more about it, and that's why I have to think about it before exam. Because if you were to think about this in exam, you will lose a lot of time. So think about it now. Think about it.